The Mandelbrot set has always been a fascination to mathematicians and curious individuals for as long as it has existed. Its beautiful intricacies and never-ending structure leave one amazed, and possibly curious as to how it's even made. But this video will go further, touching on the infinite family of what I like to call the Mandel-Not sets. But before we get there, we must take a tour through what the Mandelbrot set even is. First, I must introduce you to the imaginary constant I in complex numbers. I is equal to the square root of -1, which on first glance seems, well, imaginary. Square roots are inherently supposed to take non-negative inputs, but it seems that when we extend our minds to the world of imaginary numbers, some beautiful things can occur. A complex number is a combination of both imaginary and real parts. For example, 4 plus 3i has a real part of 4 and an imaginary part of 3i. Now here's where we start to get creative. Imagine the regular Cartesian coordinate plane with the x and y axes, both containing real numbers. What would happen if we just made every number on the y-axis an imaginary number? Well, now we've created a complex plane, which contains all the complex numbers. At the heart of the Mandelbrot set is a certain complex valued function that we call f of z equals z squared plus c, where z and c are some complex numbers. For the sake of explanation, let's let c equal 1. All this function does is take, for example, the complex number z equals 2 plus I, and says f of z equals 2 plus I squared plus 1. This works out to be 4 plus 4i. And so we have performed a transformation on z, and outputted some new complex number. The first step of the Mandelbrot set is to do this process iteratively. Don't fret, it's actually quite a simple operation. First, we need some starting value of z, and for the Mandelbrot set and all Mandel-Not sets, this z initial, or z1, will be 0. Here's where the iterative part comes in. Now we take z1 and plug it in f of z, and it outputs 1. This 1 is the next term of our sequence, and we call it z2. Plug z2 into fz and you get z3. All this does is create some infinite sequence of complex numbers, where to get to the next step, you just apply f of z. Don't worry, because the magic is about to happen. All it will take is a step back to our complex plane. Consider we go through every point in the complex plane and we set our c value to be that point. After that, we calculate a decent amount of terms in our sequence of z's, but we, just like Mandelbrot, notice something interesting about certain z values over others. It seems as though when we choose certain c values, like 0.3i minus 0.5, our sequence seems to stabilize towards some complex number. But when we choose a c value like 1 plus I, it seems to shoot off toward infinity. What if we colored every c value that seemed to stabilize black, and at every unstable point some other color? And that is what created the Mandelbrot set. The Mandelbrot set in its purest form is a way of identifying which points are stable and which points are unstable, but in this effort it creates something incredibly mesmerizing. Hopefully if you've followed thus far, you'll have a pretty good understanding of the Mandelbrot set, but I myself was not fully satisfied with this. For there is one thing in this entire process we have seemingly taken from on high, and that is f of z. Why should it be z squared plus c? Couldn't it be some other equation? It happens to be that the answer is just as interesting as the Mandelbrot set itself. Just as we expanded our minds into the world of imaginary numbers, let us once again expand into a vast world of possible Mandel-Not sets. Here are some of my favorites. Thanks for watching.